Welcome to the Biomed Faculty Campus Seminar on Mechanical Engineering. Today we have with us Dr. Todd Bredbenner. He's from Southwest Research Institute in San Antonio. He got his PhD in 2003 in Mechanical Engineering from Case Western Reserve. And then he pursued postdoc, NRSA postdoc fellowship at Case Western. And then he moved to Southwest Research Institute in 2005, where he started as a postdoc, and he's been there since. He's been in the materials engineering department there. And currently he's a senior research engineer at SWRI, and he also holds adjunct appointments in orthopedics at UT Health Science Center and biomedical engineering at UT San Antonio. With that, Todd, it's all yours.
Thanks. So I'm going running into the chair. First I'm going to apologize if I cough in the middle of it. I guess we all seem to have coughs. So I'm going to talk about the role of composite trace in understanding fracture. And this is part of the work that I've been doing, and I'm going to talk about where I think the work can head. And I guess I'll start with, I'm not from academics, so let me talk about Southwest Research Institute for a minute. We're an independent or private not-for-profit research organization. We focus on applied research and development in physical sciences and engineering. We have about 2,800 staff members currently in 10 broad technical divisions. In these different divisions, we've got sensors on the Mars Curiosity Explorer. We did a lot of the return to flight work for the Space Shuttle program. And we actually used to have the scientist that invented clumping cat litter before he died. We've been in operation for about 7 decades, nearly 7 decades. And in fiscal year 2015, which just ended in October, we had $592 million in total revenue. So I'm in the mechanical engineering division within the in the mechanical engineering division, then the materials engineering department, and then the musculoskeletal biomechanics section. There's 7 of us in the musculoskeletal biomechanics section, and I'm one of the 2 senior members. So I am going to start the other way. I'm going to start my talk with a brief description of the current U.S. population. And let's move a little bit so we can see. So the current U.S. population is about 320 million people, with almost the same number of men as women. My little figures here. So these are minorities. So you can see boys and girls, I guess is a better way to say it. About a quarter of the population is under the age of 18. And then these guys in the middle are 63%, roughly 2/3 of the population. They're adults younger than age 65. And currently we've got 14%, so there are 100 total people here, and 14% are age 65 years or older. So the U.S. population is and has been increasing. So this is the current population, and this is projections for year 2030. As you can see, the minority population stays about the same, just a little bit less. The mid-level adult population, middle-aged adults, young to middle-aged adults, roughly the same, a little bit smaller. But all these people that have been subtracted from these other groups are now in this elderly population. So 20% by the year 2030 will be 65 years of age or older. And you can also see the general population increases from about 320 million to about 360 million. So the point is that the population is aging in this country, and it's projected to do about the same for countries around the world. So if we go back to the current U.S. population at the top, so now it's what we're really concerned about in terms of fracture risk are all the people over age 50. So 1 out of every 3 women over the age of 50 will suffer an osteoporotic fracture of the hip. They lose bone through osteoporosis, right? And so they go on to suffer an osteoporotic fracture of the hip, the spine, or the wrist. Those are the 3 main areas or sites of fracture. And then 1 out of every 5 men will also suffer an osteoporotic fracture. So if we focus, like I said, on the population that's 50 years or older, the individuals that are shown in red here will go on to suffer a fracture. So that amounts to about 28 million individuals now, and it's projected to increase. Down here you see the shift, and we've got more of these individuals that are now older. Like I said, the population is aging. So right now, about 28 million people suffer a fracture before they end their lives, or before their lives end, I guess is a better way to say it, and that's projected to increase to about 36 million people in the next roughly 14 years. So by the year 2030, projections say that 1 out of every 10 people in the U.S. population will be at imminent risk for suffering an osteoporotic fracture. So osteoporotic fractures are a major public health concern. They've got current costs around $21 billion, and those costs are projected to increase in the next 14 years to about $27 billion. They have an economic burden that's immense, but these fractures are also a significant cause of morbidity and mortality in the aging population. 4% of hip fracture patients die during the initial hospitalization following fracture, and 24% will die within the first year. 40% of those that survive will be unable to walk without assistance, and 1/3 of those people that suffer a hip fracture will be totally dependent or in a nursing home in the year following their fracture. So we can talk about economic burden, we can talk about population statistics, but at the end of the day, it's the individual that matters. We need to understand why these individuals in particular are suffering a fracture, and we need to understand what we can do to prevent those fractures from occurring in the first place. So the questions are, what makes these individuals different from the individuals that don't suffer a fracture? And then the other thing to note is that these individuals are different from each other, and they may fracture different bones, or they may have different mechanism for fracture, or different events may cause their fracture. So of the group that fractures, why are they different within that group? They're different certainly genetically, they're different by body type and sex, but so much of my research is guided by these questions of how are the individuals that go on to suffer a fracture different from each other, and then how are they different from the individuals that don't suffer a fracture. So if we start to formalize the problem of fracture risk due to bone mass loss or bone quality, the first step is to accurately determine which individuals are at risk for fractures. So we need to diagnose the individuals that are at risk, and even better, we need to understand why each individual is at risk for fracture. Once we improve the accuracy of diagnosing the fracture, we begin to understand the specific condition that leads to that individual suffering a fracture, then we can start move towards treating the individual or individualizing treatment. A one-size-fits-all approach or a one-drug-fits-all approach is not likely to be productive. So the questions are, how can we look at the individual and determine which deficiencies are likely to lead them to suffer a fracture? And once we begin to understand why that individual is projected to suffer a fracture, then we can begin to understand how to treat that individual. And finally, we can improve the accuracy of diagnosis, and we can start to individualize treatment protocols to prevent fractures. But we really need to move from the research problem to the clinical problem. If the proverbial little old lady or little old man walks into the clinic, how can the understanding and the technology that we can develop in our research projects be used in the clinic to diagnose and treat that specific person? They have a right to care about their condition and their situation, certainly, and my work is moving towards providing a better understanding of why fractures occur and how we can prevent them from occurring in the first place. I'm going to focus most of my talk on the diagnostic piece and what I've done in terms of improving the accuracy of determining which individuals are at risk for osteoporotic fractures. I'm also going to touch on how we can move towards individualizing treatment in a more productive manner, and then how we can move towards implementing these ideas and this knowledge in order to prevent fractures from occurring in the little old man or the little old woman that walks into the clinic. So the clinical standard for determining fracture risk is shown. It's an image of DEXA, dual X-ray absorptiometry. Basic idea is you go into the clinic and get a bone scan. It's an X-ray based procedure, and some technician pushes a button and it spits out your bone mineral density, and then it's compared to the same, our young adult population of your sex and your race. And relative bone mineral density indicates fracture risk. So it does reasonably well at explaining some proportion of the fracture risk, or some portion of the fracture risk, but it doesn't do great in terms of understanding the individual, and I'll go on to talk about that more at the beginning, or in a minute. And so the other thing we could do is to look at QCT image. So CT, or computed tomography, is fairly standard in the clinic, but quantitative CT, where the subject or the patient or the individual lies on top of a density calibration phantom, and then you collect CT data for their hip, or their spine, or their radius, or whatever, is not as common. It's not terribly difficult, just a little bit more training is required, and there are always questions about healthcare reimbursement, things like that. But the advantage is here, rather than projecting bone mineral density into an aerial measure, the amount of bone within some area, here we can start to look at the distribution of bone mineral density. We could do things like separate cortical bone from trabecular bone, and a lot of the knowledge in the past has been that people lose trabecular bone faster, so loss of trabecular bone may lead to indicating fracture risk better. Some of the current knowledge is moving more towards, well, cortical bone loss also plays a role. So I'm going to illustrate a few points throughout the talk using some data that I generated using a sample of older men from the osteoporotic fractures in men study, or Mr. Oss. This was an epidemiological study. Eric Orwell at the Oregon Health and Sciences University is a PI. Mr. Oss is a multi-center epidemiologic study, like I said, consisting of about 6,000 community-dwelling men aged 65 years or older. The purpose of this study is to investigate the determinants of fracture in this population of older men. So I used imaging data, QCT imaging data, so I used imaging data that was collected at the beginning of the study, aerial bone mineral density. Bone mineral density from DEXA was available for all these individuals. This study consisted of, this sample consisted of 450 older men, 40 suffered a fracture at some point within about a 6-year follow-up period, and 410 did not. So on the y-axis here is their aerial bone mineral density. And you can see that there's this big spread. All the individuals with blue, or the bone mineral density for the individuals that do not suffer a fracture, are shown in blue. The individuals that did suffer a fracture are shown in red. In terms of population statistics or sample statistics, there are significant differences between the two groups, but if you look in this region here, for instance, you can't draw a cutoff line. So there's a lot of separation within this range in particular, and so you can't use bone mineral density as a very good indicator, a very accurate or specific indicator of who's going to go on to suffer a fracture. So we've also got, this is that same slide, but now we've got these 3 individuals that have amongst the highest bone mineral density. So we've got the same issue. So on a population level, we could argue that bone mineral density does a reasonably good job of differentiating between those that are going to suffer a fracture and those that won't. But we look at the distribution, and on an individual level, it doesn't do a very good job at all. It's just not accurate. It's not specific. I talked about volumetric BMD in terms of QCT data, and here we've got the same issue. These same 450 men, again on a population statistics basis, there are significant differences between the mean of those that suffer a fracture and the mean of those that don't in terms of bone mineral density, volumetric bone mineral density, but we've got this overlap again. So even though we're moving towards a better indication, we can get more data. Now we were describing a 3D situation. We still can't pick a cutoff line. We can't do a very good job of determining which men are going to suffer a fracture and which won't. And so I'd suggest that this approach of using or trying to directly correlate imaging data with fracture risk is inaccurate. It's a dominant approach used in the clinic, and in fact it's generally the only approach used in the clinic. The bone is a structure, and it may be more complicated than a bridge or a building because it's a living material, it's a living thing. changes. Lots of things are going on, but it's still a structure, and the fracture of bone is a mechanical process. So it seems likely that accurate identification of the people at risk are going to maybe interpret imaging data using some consideration of bone being a structure in order to determine fracture risk. So we're going to take into account the structural organization of the bone. If we look at these same 450 individuals, so on the left I'm showing surface geometry. It's a fringe plot. Both of these plots, so on the left is surface geometry, on the right is the mid-plane bone mineral density distribution. All these plots are showing point-wise differences in terms of the color scale. And for the fracture femur relative, so the mean fracture femur relative to the mean femur for the individuals that did not go on to suffer a fracture. So if you look at the geometry, for instance, there are these large changes in geometry. So at all these points that are towards the red end of the scale, the fractured group is larger than the individuals that did not suffer a fracture. We also see changes like there are people that have tried to use simple measures or discrete measures of geometry, where, for instance, we've got the axis between the angle between the femoral neck axis and the shaft. So that angle maybe looks like it's shifting for the individuals that suffer a fracture than with respect to those that don't. If we look at the mid-plane bone mineral density distribution, but certainly cortical bone, you can see these big decreases in the individuals that go on and suffer a fracture. A lot of this region, though, there's not that much change. And in some regions, there's even more bone mineral density in some spots. So I'd argue that the structural integrity of any bone is dependent on the size and shape of the bone, on the spatial distribution of BMD, for instance, and then on complex and interrelated cortical and trabecular bone characteristics. On the right is a micro-CT image, or a slice of a micro-CT image, and we can see, so there's distribution of microarchitecture. You can see the trabecular cascade where cortical bone is transferring load from the femoral head down to the shaft, but you've got this trabecular cascade. It's also transferring part of the load along this cascade down to the cortical bone. And so it's a complex it's a complex structure, and we need to begin to understand the structural organization, I would argue, rather than look at individual traits or simple combinations of these individual traits in order to successfully classify fracture risk. So I wanted to test the hypothesis that the structural combination of individual traits or composite bone traits would determine the resistance to fracture, and therefore a description of structural organization will improve the accuracy of identifying those that are at risk for fracture. So I took the same QCT data. I processed it using a continuum level approach, so we're just focused on bone mineral density distribution, rather than the resolution of QCT won't let us get down into trabecular microarchitecture, things like that. So again, we've got 40 fracture cases, 410 non-cases, and in all the analysis, or in all the processing at least, we were blinded to hip fracture status. Started with QCT data, segmented that data to separate the bone from the background, and then generated femur surfaces for each of the individual sets of data, and then went on to sample the bone mineral density at each of these volumetric nodes. We took these surfaces, created 3D volumetric meshes, same form as a finite element model, and then sampled QCT data at each of the locations of the nodes. So we ended up with 450 3D volumetric models that describe the geometry and the bone mineral density distribution of the right proximal femur. And each of these models consisted of about 57,000 variables that were the spatial locations X, Y, and Z of each of the nodes, and also the BMD at each of the nodes. There are about 14,000 nodes. So we took another step here where, so if we just have all these models, we can't directly compare them. So we enforced model correspondence. So that means that the mesh nodes are located at corresponding anatomic positions for all 450 proximal femurs. These colored dots mark the same node ID for each of the femurs. So you can see that the orange dot, or the node with an orange marker exists at the top of the greater trochanter for each of these femurs, even though they're different shapes. And the same for the other colored dots. So we took a set of template nodes, and they were mapped onto each femur. And then, like I implied, or like I suggested, I guess, the template nodes were repositioned on each femur so that they did have anatomic correspondence. And so now we've got a set of 450 models that we can compare directly to each other. They describe the geometry in terms of the outer cortical shell, and they also describe the bone mineral density distribution within the femur. We use statistical shape and density modeling, or statistical shape and trait modeling. It's a little bit more generic, but it described the variation in bone geometry and density distribution within this QCT data for the set of individuals. It was based on a principal component analysis, and it's an unsupervised method of variable reduction. So I'm not biasing the outcome or the determination of the models in terms of any functional outcome. You let the model sort itself out, you let the data sort itself out, and it separates itself out into these inherent combinations of traits. So whereas we started with a bunch of traits, locations at each node and spatial distribution of density, that's all highly correlated. Now we've gotten rid of that correlation. We can talk about independent composite traits, but we're still retaining all of the information in terms of geometry and density distribution that we had in the initial set of models. But now we've got this relatively small set of uncorrelated and independent variables. And so each individual femur now can be described in terms of the average femur and a set of weighted linear combination of these composite traits. They're called these inherent combinations of multiple traits. And so now the weighting factors essentially, well, the weighting factors do carry all the variability within the set of the models. So for the set of 450 femurs, like I said, all the variability is now described by the weighting factors. On the x-axis, it's just an ID for the composite traits. And on the y-axis, this is the total variance explained cumulatively for each of, cumulative combinations of these traits. So all 449 of the variables explain 100% of the variance in the set of 450 femurs. The first mode explains, or the first composite trait explains about 22%, and let's see, so 329 explain 99%, and 53 of them explain 90%. I used logistic regressions along with variable selection methods in order to model the relation of the principal component weighting factors to the subsequent occurrence of fracture. And then in order to minimize the possibility of overfitting or bias in the model development or in the predictor development, I used a nested tenfold cross-validation scheme. So the 450 men were divided into 10 equal-sized groups. 45 each had 4 fractures in it, and 41 individuals that did not go on to suffer a fracture within the follow-up period. And so 9 of those sets were used as the training set. Here, where we took the training set, we knew their fracture outcome. We iteratively defined a classifier. And then we took this test set that, as far as this classifier is determined, is unknown, right? So we use these individuals, substitute them into the classifier, and we predict whether they're going to go on to suffer a fracture or not. We bring in the test set fracture status and determine whether we were right or not in terms of reliability and accuracy. And this process was repeated 10 times to get the 10 folds. So all of the individuals were used in both the test set and then 9 times in terms of or in the training set. So I also, I did this for the weighting factors, but I also did this for total hip aerial BMD, age, and BMI, using them as adjustments for BMD to see if there was any relationship there. I did it for the composite trait weighting factors also adjusted by age, BMI, and aerial BMD to see if there was overlap. If I look at so here's a little bit different picture of the composite traits. Now I'm showing the total variance that's explained by each individual one. So we go back to the first individual trait, explains about 22% of the variance. And all of the traits are shown here either as a black dot or a red dot. The red ones are selected in the predictor, and the black dots were not. So because we did this 10 times, on average, 23.6, roughly 24 of the 449 shape modes were selected, and that cumulatively explains 53.8% of the variance in the system. So we could talk about reliability. One of the things that's commonly done in clinical data is the area under the receiver operating characteristics, ROC curve, area under the curve is AUC, and so this was used to determine the predictor reliability. So in general, aerial BMD, clinical-based methods are shown in black, the black family of curves here, and in red, the statistical shape and density modeling-based family of curves, adjusted by age and BMI. By age, BMI didn't have any effect here, and then age and BMD. So now we can look at the area under the curve, and these are the 95% confidence intervals for that area under the curve, based on this 10-fold cross-validation scheme. And now there are significant differences between the clinical method and the statistical shape or composite trait-based methods. So these methods in general, or these methods, regardless of age or BMI, age or BMD adjustments, are statistically better at predicting which individuals are going to go on to suffer a fracture and which are not. Excuse me. So we also looked at the 10-fold cross-validation sample in terms of predicting individuals. So we talked about correct classifications, which was, all of the individuals in the test set, 45 men times 10, and these are, again, in the black, are the aerial BMD-based measures, predictors, and the composite trace-based measures in red. And so there's no significant differences. Qualitatively, there aren't any differences, and they're not significant between any of these in terms of overall correct classification numbers. The same thing with the non-case classifications. But if we focus on the correct fracture classifications, now these are the ones we want to identify, right? We want to do better in determining who's going to suffer a fracture so we can treat those people. In black, we've got the area BMD group, and in red, we've got the composite trace-based group. So if we look at the percentage of correct fracture classifications for the fractures in the test set, each of the test sets, the best one involving area BMD gets about 15%, or we get 55%, so about a 4-fold increase if we use composite traits. So we're describing the structural organization, and that looks like it's leading to more accurate, and here you can see those two values just by themselves, but by accounting for the fact that there's variation in structural organization, we can do a better job of identifying the individuals that are going to suffer a fracture. Well, so far, so now we're at about one out of every 5, and that's not great for the individuals that walk into the clinic, but so far, this is the hierarchy of fracture. So, we've got hormonal or genetics or biochemistry biomarkers on this side, and sorry for the reverse of what's normal, but these molecular level characteristics or traits in individuals go on through the hierarchy up to the level of a whole bone, here a whole femur, and the microstructure within that bone, and then that bone certainly is part of the whole body. So this is the whole multi-scale hierarchy of a fracture. And all the work I've shown to you to date, all I'm doing is looking at the bone by itself, right? So there's all this other variability that we're not taking into account. So by looking at just the bone, and it's a continuum level approach for the bone because we don't have, at least in clinical data, we don't have resolution that's good enough, say that's a reasonable statement, then but I can still do better than the current clinical methods. So by incorporating variability in some of these other areas, then maybe we can do even better. If a person, things like stability, if a person doesn't fall, then they're not likely to break a bone, right? There are a number of other things, and I'll talk a little bit more about them. So quickly, I've done the same sort of thing with vertebral fractures. So this is a set of data that I got from Sandeep Khosla at the Mayo Clinic, and it's about 80 individuals. Half of them were men, half of them were women. They're all elderly individuals over, I think it's over the age of 60. But they were age matched at least. BMI matching was a little bit harder. But so half of these men went on to suffer a fracture, half did not. Half of the women went on to suffer a fracture, half did not. So on the left here, we're looking at geometry differences. And again, so for the females, for instance, all the blue regions for the individuals that suffered a fracture are smaller than those that didn't suffer a fracture. But, so they're getting smaller geometry as they age, and they're getting these increases in bone mineral density to try to compensate for that. And something different happens with the males, right? So males are compensating in terms of they're losing some bone. Overall, they're losing bone, but they're increasing the size of their vertebrae. And so that's what we can show here. And these patterns are representative of anecdotal things that happen in the clinic. But we can also then go on to look at composite traits, and we can get a set of composite traits or weighting factors for composite traits that will identify which men and which women go on to suffer a fracture. And the interesting thing is that those traits, or those sets of traits, are different between men and women. So that makes some sense. But it looks like composite traits, based on this preliminary work, will differentiate between males and females that go on to suffer a fracture and those that will not. Diabetes is another disease where bone changes. It's interesting, it generally increases bone mass rather than decreases bone mass, but it changes the quality of bone. So type 2 diabetes is, secondarily, lots of people suffer fractures just because they have type 2 diabetes, and it changes the quality of their bone. And this isn't all that well understood. Like I said, people have greater bone mineral density on these simple measures, but they go on to suffer a fracture anyway. So this is a study with some data from Thomas Link at UCSF, where, so on the top we've got geometry comparisons, on the bottom we've got midplane density comparisons, and I'll walk you through. So this column is the control group. So here we had a control group and a type 2 diabetic group. Half of each group went on to suffer a fracture, the other half did not. So the controlled fracture group versus the controlled no fracture group, things we talked about a little bit before, you can see some, they're actually